Everyone did good on their exams. I think the average was 80, 81, 82, somewhere in the 80s. So it's fine by me. Okay? So everyone did a good job. Just keep it up. Some of you did really well. And so, yeah. All right, so let's balance some chemical equations. I'll do a couple of these, and then, like I said before, I'll post the answers up or give you the answers on Thursday. All right, I don't know how to teach this. I don't know how to teach this, even though I'm your teacher. The only thing I can tell you is just do some trial and error. Okay, just do some trial and error. So we'll do the first one here. KClO3 goes to KCl plus O2. Right, so this here is called the reactants. Okay, to the left of the arrow. This here to the right of the arrow are called products. So reactants go to products. Reactants go to products. Okay. We need to balance it out. Okay, the way you balance it is you never, okay, don't do this. You never change these numbers. Okay, the only way to balance it is by putting numbers in front. Okay, we put numbers in front of the chemical. Okay, you don't change the 3 in O3. You never change the 2 in O2. I've seen this happen before. We don't want to do that. You only put a number out in front. You can also put fractions. Okay, you can also put fractions. I think we'll go over some of those. So I just say trial and error, and let's see if we can do that here. Okay, so the reactant side, we have K, we have Cl, that's chlorine, we have O is oxygen. Product side, we have K, Cl, oxygen. Everything must be accounted for. Okay, everything, every atom must be accounted for. Okay, so anybody want to guess? There's no wrong answer. Okay, how would you want to do this? Okay, like I said, I don't know how to teach this other than trial and error. So what do you guys think? So Gerardo, right? If I put a 2 here, again, trial and error. Okay, that's 2K, 2Cl, 6 oxygens. Okay. If I put a 2 here, I get 2K, 2Cl, and what can I put here? 3. Okay, for some people this comes. For some people it just takes some nudging. Okay, so 2Ks, 2Cls. Okay, we have 6 oxygens. We have 2Ks, we have 2Cls, we have 6 oxygens. Okay. How about this one here? Fe plus Cl2 goes to FeCl2. What do you think? Is that balanced or does it need balancing? You are correct. It is already balanced, right? You can see that here. 2 Cls, 2 Cls, 1 Fe. All right, how about this one here? Okay, let's do a couple of more and then I'll give you the answers in our next meeting. Okay, C4, H10O2 plus oxygen goes to CO2 plus H2O. Okay, this is number 3 here. Okay, by the way, this is called a combustion reaction. Anytime you see a CO2 and water and one of these carbon, hydrogen, oxygen molecules with oxygen, we call it combustion. This is not something you need to know now, but I'm just, it's combustion. right, how many carbons do we have here? Hydrogens and oxygens. How many carbons? 4. How many hydrogens? Oxygens. What about carbons here? Hydrogens. 2, 3. Okay. All right. To me, I like to balance this last. Why? Because it's a loner. See, if I put a number here, that's going to mess up hydrogen and oxygen. But if I put a number here, it's only going to mess up oxygen, and I can do it at the last. You know what I mean? It's kind of like the last thing to balance everything out. So I like to balance the loners last, if I were to give you a trick. But what do you guys see here that comes out to you? Again, there's no real wrong or right way to do this. Okay, what do you think about the carbons? Okay, 4. And what will that do to my oxygens? 8 plus 1 is 9. Okay, what's the next apparent thing? 5. Okay, that's going to make hydrogens 10. What are my oxygens now?
8 plus 5 is 13.
8 plus 5 is 13. All right. How will we get to 13 here when we have 4?
13 minus 4, that's 9.
But Husong, if I put a 9 here, 18 plus 2 is 20.
2 over 9.
If I put a 2 over, well, it's a fraction, but what fraction will that be?
9 over 2.
If I put a 9 over 2, the 2's cancel. What's 9 plus 2? 11. So what should I put? Not 9 over 2, but
11.
okay, so you can't put fractions in there. Okay. Everybody see the 11 over 2? 11 over 2. All right, so 11 over 2, let me tell you why. You see this 2 and this 2 cancels, giving you 11. 11 plus 2 is 13. You can also do another thing. You can do like they do in math and algebra. You can multiply both sides of the equation by 2. Okay, so I kind of like multiplying both sides of the equation by 2, but you can leave it as a fraction. That's not a problem. So if I multiply both equations by both sides, like in math, by 2, I'm going to get 2C4H10O2 plus 11 oxygens, 8 CO2 plus 10 H2O. Okay. So just be careful that you may come across fractions, especially if you have those odd numbers. All right? And you can multiply, like in algebra, both sides. Okay? Does everyone get this? Okay? If not, you can see me during my office hours. All right, let's just double check and make sure we are correctly balanced. CHO. Okay. Okay, how many carbons do we have? 8. How many hydrogens do we have? 20. How many oxygens do we have? 4 plus 22 is 26. How many carbons do we have? How many hydrogens do we have? 20. And then how many oxygens do we have? 16 plus 10, 26. So this is how we will balance this equation. Okay. So just got to do some trial and error here. All right, so we did this. This is already balanced. We did this. Let's do another fraction problem. Let's do number 8. Okay, let's do number 8 here for a second. All right, I'll copy down number 8 and let's do that together. Okay, we'll do 2 or 3 more. CH3, CH2, CH2, CH3. Hey, where are you? Here you are. Okay. All right, this is another example of a combustion reaction. Okay, combustion, reacting with oxygen, giving you CO2 and water. All right, we have carbon, hydrogen, and oxygen. Carbon, hydrogen, and oxygen. How many carbons here? They don't get blurry on me now. 1, 2, 3, 4. How many hydrogens? 3 plus 2, 5, 7, 10. How many oxygens? 2. How many carbons?
1.
Hydrogens 2, oxygen 3. What do you guys think? Me, if it was me, I would go for the carbons. Okay, I'll put a 4 here. If I put a 4 here, my carbons are balanced. And now I have 8 plus 1 is, what's 8 plus 1? 9. That doesn't look so good. Hydrogen 10, what can I do here?
5.
5, okay. So 5 times 2 is 10. And now I have 8 plus 5. Okay, 8 plus 5 is 13. Okay, so how will I get to 13 here? 13 over 2. Okay, is this something you guys see? Okay, you can put fractions in there. 13 over 2.
Just a quick question.
Yes,
So
sir.
when we see that long thing, CH3, CH2, blah, 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 blah,
Okay.
can we just like write it on the side, write it as C4H10?
You can. Yes. It's another way of writing it.
It's easier to read.
Yeah, this is called butane. So they write it like this because they want you to show that it's butane. Uh-huh. Yeah.
Are you getting when you're starting to multiply like carbon 4, are you getting it from the left side to the right side?
Yes, sir.
Numbers?
1 carbon, 2 carbon, 3 carbon, 4 carbon.
And you're putting it on the other side in front of the seat. So you're always going to get whatever's on the left be in front of what's on the right.
Yes.
Okay.
And you only put numbers out in front. You don't change the bottom numbers. You never change that. If you change the bottom numbers, you're changing the actual formula. Okay. Yeah. All right. So 13 over 2. Okay. 13 over 2. All right. So this 2 cancels out with this 2 mathematically. Mathematically cancels. Okay, it doesn't cancel in terms of the chemistry, just math. Because somebody said, a long time ago, oh, now I have 13 oxygens. No, you don't have 13 O's, you have 13 half O2. It just so happens that this 2 and this 2 cancel out. Math, not chemistry. Okay, so never mess with this number. Okay? Let's multiply both sides by 2. Okay, so if I like math, so this will be 2 CH3, CH2, CH2, CH3. Okay, 2, and the 2's 2 cancel, that's 13 oxygens. 8 CO2. 10 waters. Okay. This is our answer.
If we were asked to, well, if we end up dividing like the 13 over 2, we need to then multiply it by 2.
Done. It's fine. Yeah, yeah, it's okay. If you want to leave it like this, that's fine. If you want to put it out like this, that's even better. Okay. How about we do 2 more? We'll do 6 and 10. Okay, 6 and 10, and then the others I will give you in the interest of time, I will give you the solutions. All right, MnO2, let's do number 6 now. MnO2 plus H2SO4 goes to MnSO4. This is manganese 2 sulfate plus oxygen. Looks like they already gave you the 2 waters. Okay, 2 here. All right, this is number 6. Okay. All right, let's try this one out here. Okay, reactants goes to products. All right, so I'm going to do Mn. I'm going to do oxygen. I'm going to do hydrogen, and I'm going to take this out just to make things easy. Okay, this is called sulfate, so I'm going to take it out as SO4. Okay. MnO, hydrogen, and then SO4. Okay. So you can do that. You can pluck the SO4 out. Okay, this is called sulfate. Actually, sulfate is SO4 minus 2, but I'll take the SO4, which is a polyatomic ion. I'll take the SO4, which is a polyatomic ion. Okay. All right, how many Mns do we have? 1. How many oxygens do we have? Oxygens. Okay, I'm going to take this out as 1 unit. Okay. Okay, it just makes it easier. Okay, I take it out as 1 unit, SO4. How many hydrogens do we have? How many SO4s do we have? Okay, this is called sulfate. Okay, how many Mns do we have? How many oxygens? 2 plus 2 is 4. How many hydrogens? How many sulfates, SO4? Okay, good job. Okay, 1. All right, what do you think we can do here? Any ideas?
We can double the H2SO4.
If you put a 2 here, that makes that 4. That makes the SO4 2. Okay. And then if I put a 2 here to balance out the SO4, Husam, that gives me 2 SO4, and then I'll put a 2 here to balance out the Mn. And that gives me 4 oxygens. Yep. That's right. Okay. Yes, sir.
So why did you divide it into sulfate to the sulfate oxygen?
I mean, I could also put it as, it's just for ease. I can put like I can do MnOHS, and I can do it like separate them out. But it would be easier if I take this as 1 unit. This is called the sulfate ion.
So,
Yeah, you can do it like we've been doing before, but this is easier.
so both Mn and SO4, because Mn is also equated like Mn and Mn,
Yeah.
they're all the same, so they count as just only one, right?
Mn and Mn is the same.
The same as
Ah.
SO4? Like in
Yeah, SO4 is, remember your flashcards? Or SO4 is called sulfate. Yeah. Actually, it's SO4 minus 2. Here it becomes minus 2 to form H2SO4. So, yeah. So, all I'm saying is that you can take it out. You can take out the sulfate. If you can take out the phosphate. You can take out the nitrate. You can. Okay? But if you don't feel comfortable, you can do MnOH and then have, count them as we were doing before. Okay, shall we do one more, or are you guys comfortable with this? Good. All right. Are you guys okay? I need a yes or a no from everyone, not just one or two people that are active. Yes? Who says yes? Who's aye? Who says no? Okay, I know people are not saying no because they're too shy. So. All right. You can see me in my office hours, and I'll post the answers up for this. Okay? Any questions or comments? Right, we need to balance equations in order to do something called limiting reactants, limiting reagents. All right, do you remember the example here in the notes? Okay, let's say you have you have 5 females and 2 males, okay? And they partner 1-to-1. Okay, which gender is in excess? Okay, 1-to-1. So we have females are in excess. And then gentlemen or men are limiting. Okay, let's say they're doing a dance, a 1-to-1 dance. Okay, 1 man to 1 woman. Okay. How many dances can you have?
For each male, there can only be 2 females.
Yeah, nothing strange. Just 1 man, 1 woman dance. Okay, how many dances can you have? 2. Okay, how many females are left over? Who are all gone? Used up? The guys are used up, okay? Guys are used up. The guys are all gone. Okay? So in this way, the men determine how many dances you can have. Okay, the men determine how many dances you can get. Okay, you'll have 3 females without a partner. Okay, so men are limiting, females are in excess. You're only limited by how many. You only get 2 dances because you only got 2 guys. Okay, and the rule I made is 1-to-1. Right, the same way a reactant gets used up. If it gets used up, that's how much you can get. The reaction stops. Okay, whatever the other reactant is in excess. So you'll have a problem like this on the test. So it may be worth doing this one just together. Okay. And another thing I need to tell you guys, a limiting reactant is a reactant. It's not a product. Okay, so when they say identify a limiting reactant, are you going to identify a product? Okay, you will identify a reactant. Okay, it's either this reactant or this reactant. Okay? All right, so it's the reactant that gets used up and it sets the limit. Okay? All right, so we'll do this problem together. Okay, so the first step you want to do is you want to balance the equation. Okay, you want to balance the equation. Okay, so we want to balance the equation. So let's go ahead and balance this. It's not balanced, so we'll balance it. Al plus Fe2O3 goes to Al2O3 plus Fe. Okay, I'm going to balance it really quickly here.
Isn't it 2, 1, 1,
2 Als and then 2 Fe, right?
2? Yeah.
Okay, 2 and 2.
So you got everything.
Okay, now we're balanced. Okay, we'll do a limiting reactant problem similar to this on the test, so it's worth doing this. Okay, so the first step is to balance the equation. Okay, the second step is to ask yourself a question. Okay, how much Al2O3 is formed? Now, Al2O3 is a product. Okay, so this reactant is going to go with this reactant. They'll react, they'll mix, and will form this product. Over time, one of these will be gone. When this is all gone, this is how much you can make, Al2O3. Okay, because once this is gone, or once that is gone, you're done. You can't make any more product. Okay, so one of these sets the limit. Okay, this is the limiting reactant, limiting reactant or limiting reagent. So we will ask how much Al2O3 product is formed when all the Al aluminum is used up. One of them is going to be limiting, the other one will be excess. Okay, so how much of this product is formed when all the Al is used up? So I will do that in green pen. Okay, green pen for Al. We have 124 grams of Al times 1 mole of Al contains how many grams? It's about 26.98 grams of Al. Okay, so what's next here? Okay, we need Al2O3. So one of the rules of the mole is you use the mole-mole relationship. So for every 2 moles of Al, this is balanced. How many moles of Al2O3 will you get? 1. Okay, and for every 1 mole of Al2O3, okay, how many grams will you get? 1 mole of Al2O3. The periodic table, Al times 2, oxygen is about 16 times 3. I went ahead and did that already. You add them up, it's about 101.96 grams. So 124 times 101.96 divided by 26.98 times 2. $234. And by the way, just want to tell you grams, moles cancel. So you got 234.3 grams. $234.3 grams of Al2O3 is produced when all the Al is gone. When all Al reactant is consumed. So this is how much you make when all of this is gone. Okay? Okay, let's see how much of the same product you make when all of this other reactant is gone, and that is Fe2O3. Right, so our next question is how much Al2O3 product is formed when all the, not Al reactant, but all the Fe2O3 reactant is used up. Okay, one of these is going to get used up. Okay, just like all the men here are taken up, one of these reactants are all going to get used up first, or taken up first. So how much Al2O3 product is formed? Okay, when all the Fe2O3 reactant is used up. Okay, we'll do that with this X mark here, okay? This black ink. So here we're starting off with 601 grams of Fe2O3. So 601 grams of Fe2O3. This is iron 2 oxide. 1 mole of Fe2O3. Okay, you take the number of iron times 2. You take the number of oxygen, which is about 16 times 3. You add them up. I did that already just to save some time. And I got about 159.6 grams of Fe2O3 are in 1 mole. Okay, what comes next? What's the mole-mole ratio? One to one. Okay. Okay, so it's a 1-to-1 ratio. So for every 1 mole of Fe2O3, there's how many moles of Al2O3? For every 1 mole of Al2O3, there is about 101.96 grams of Al2O3. Okay, remember oxygen is about 16 times 3, aluminum 27 or so times 2, add them up from our periodic table. And then the grams cancel, the moles cancel, the moles of Al2O3s cancel. All right, so 601 times 101.96. Divided by 159.6. I'm getting 383.9. Okay, let's write down this number. 383.9 grams of Al2O3 is produced when all the Fe2O3 reactant is gone or used up. Okay, so now we know how much product we produce if all of this reactant is used up. That's in the green. And then how much we produce of this when all of the Fe2O3 reactant is used up. Okay, that's in the black ink. Right, so what do you guys think is the limiting reagent? The one that produces 234 grams of product, or the one that produces 383 grams of product?
The ones that produce 240 something.
Yeah. See, once you produce this much, all of this is gone and the reaction stops. Okay? So Al is our limiting reagent. Okay? And then Fe2O3 is excess. So how much of this product can we actually make? Okay, in theory, this is called theoretical yield. Okay, in theory, the theoretical yield of Al2O3 is 234.3. Okay, that is in theory. Okay. So if we are perfect machines and robots, we can make 234.3 grams. But really, no one ever makes that because stuff spills, some things boil off, things stick to the side of the filter paper, whatever happens, things, mistakes happen, human error, whatever. So we really never get to our, in theory, based on stoichiometry, we really don't get to the theoretical yield. What we usually get is the actual yield. Okay? The actual yield. Okay? Because we're humans and we're not perfect, we can never produce, if we were to do this reaction, we would not produce 234.3. Because like I said, things spill, stuff boils off, sticks to the paper, whatever. Okay? So we have something called the percent yield, which is the actual yield. Okay, in this case, you do this reaction, and in this problem, they did it, and they got 200 grams. Okay, and in theory, what is our theoretical yield? In theory, you should make 234.3 grams. Okay, we'll multiply that by 100. And this will give us our percent yield. So this reaction has an 85.4% yield. Not bad. So percent yield. So yeah, go ahead.
So why is it 200 grand?
This is in the problem.
Oh, okay.
Yeah. It was in the problem. Part B. Calculate the percent yield. Okay. It's the actual yield divided by the theoretical yield. So this is funny. When we do the limiting reagent labs and you have to calculate this, I mean, it makes me laugh. You'll get like 1,000% yield or 1,500% yield. Okay, is that possible? 236% yield. Okay, you can only get to 100% yield. All right, so if that happens, maybe it's a math error. Maybe we didn't. I didn't heat it. I didn't get all the water away. Or something, okay? Could be some error, okay? But you cannot exceed 100%. And you can't get negatives, okay? So no negatives and 300%, you should have won the Nobel Prize. You created more matter, okay? So this thing should not exceed 100% is what I'm saying, okay? So you do your actual, in theory, based on stoichiometry, and in your actual yield is something you weigh out later. Okay, we'll do that today. I'll actually weigh them out. I'll give you your actual yield, because what I'll do is, this is for the lab, I'll put them in the oven overnight, and then tomorrow morning I'll weigh it. Okay, so, yeah. All right, are there any questions or comments on this? All right, with your blessing, I will move on to chapter 4. There's another problem here, but I worked it out in the video for your extra credit. Okay, so do that. Okay, do this. If you haven't watched the video, you can go ahead and watch it. I went ahead and did this problem. All right, I believe it. Yeah. Okay, so just another practice. You'll see one of these on the exam, and we'll also have a review, so just in case. Any questions or comments? All right, shall we move on to chapter 4? All right, here we go. I finished chapter 3. And now we're on chapter 4. Now would be a good time to turn in the chapter 3 homework. Though I changed the dates to something strange, but you can turn in your chapter 3 homework and I'll give you the points. Okay? And then remember, homework is just practice. Okay, check your answers with the answer key. All right, 30 minutes. All right, I thought I'd give you a little demonstration here, so you can just sit and relax. Here I got a beaker of water. Okay, I'm going to call this water solvent. Have you heard this term before, solvent? Okay, it's, I don't know, what do you call it? Dissolving medium, what you want to dissolve your thing in. So we're going to call this water solvent. Okay. And in this case, water. Okay, that D stands for distilled. And you know, I should tell you guys as a class that in Gen Chem, our solvent will be in water 99% of the time. I think in organic you have the crazy solvents. Okay, but the solvent is the dissolving medium. Okay, water. Okay, if I want to dissolve it in oil, if I want to dissolve it in, I don't know, gasoline, whatever. Okay, it's the dissolving medium. Okay, here I have sodium chloride. I have sodium chloride. I'm just going to put this sodium chloride in water. Before I put that sodium chloride in water, I'm going to call this sodium chloride, which looks like a white powder. It's hard to see. You see a white powder of sodium chloride. I'm going to call that the solute. Okay, it's the particle that I want to dissolve in the solvent. All right, there it goes. And does it go in? Does it dissolve? It should. Okay, you have salt water, right, in your kitchen at home. So it has dissolved. Okay. Look. You do this in your kitchen every day, so it's like, wow, no, it's cooking. Okay, so I've dissolved some salt in water, and it dissolved. You had no idea. Okay, if someone walked in here and saw this, oh, that's water. Okay, no, it's not water. It's water with some sodium chloride dissolved in it. And what we've done is we've created a solution. Okay. So the first thing here is that a solution is solute plus solvent. Okay, solute plus solvent. Now the sodium chloride dissolve in water. What do you think, Emily? Yes, right? Okay, what do you think, you guys? David? Okay, it dissolves in water. Okay, so we say sodium chloride is soluble. If it didn't dissolve, what would it be called? It would be called insoluble. Insoluble. But sodium chloride is soluble. Okay? So we have solvent plus solute is equal to solution. Because my solvent is water, okay, because my solvent is water, we will call this a special type of solution, and we will call it an aqueous solution. Okay? An aqueous solution, if it dissolves, it will be where the solvent is water. Aqueous, aqua, water. Okay, and that is AQ. Okay. So we have a solid, we have liquid, we have gas, and now we have aqueous. Okay, these are states. Okay. So an aqueous solution is when the solvent is water. Distilled water. Okay. Right, I have another solute here. This one is sucrose. Sucrose is like sugar. It's basically sugar. Okay. You can see it. It's also white. It's a little bit more powdery, like powder sugar. Okay. Talking about some physical properties. I'm going to put this here. So I put this solute in this solvent. I've made a solution. Let me stir it up. Okay, does it look like to you that it has dissolved? To a certain extent. So there is my sucrose in water. Okay. So I've also made a solution here. Okay. So. Okay. So sucrose is another form of a sugar. So even though they're not exactly the same, I'm just going to call it glucose. Even sucrose is just glucose with something else, but I'm just going to call it another sugar, and that's glucose. Okay, so the formula for glucose is not NaCl. Okay, it's C6H12O6. Okay, so a major component of that sucrose that I dissolved in water is glucose, which is C6H12O6. This is not something you need to know. Okay, all you need to know is that I dissolved it in some water and I've made a solution. Okay, it has dissolved. Okay. Do I see any floaties? A little bit. Okay. And once I get all the floaties out, then it's dissolved. So I got sugar water, which contains glucose. I have sodium chloride water, salt water, and essentially sugar water here. Okay, so I made two solutions. Do you agree with me? Okay, they both dissolved. This is dissolved, though it looks a little cloudy, but it's dissolved. And this has definitely dissolved. Okay. So do you think sugar or glucose is soluble in water? Okay, it is soluble. Okay, it's soluble. So glucose, C6H12O6, is soluble in water. So, do you guys remember from chapter 1 or chapter 2 what type of compound is sodium chloride? Is it ionic or covalent? Okay, very good. It's ionic. What do you think about the glucose, which is in the sucrose water, sugar water? Is it ionic or covalent? This thing, C6H12O6. Covalent. Okay? Say it with more confidence. Okay. Covalent. Is it covalent?
Yes.
Yes? Is sodium chloride ionic? Is glucose in there covalent?
Yes.
Yes. Not sure, yes.
Yes.
Oh, sure. It's yes. Okay, this is covalent, and that's ionic. Okay, an ionic substance contains what? It contains ions. Okay, do you know anything about ions in terms of what are they? They're charged particles, right? Charged particles. Ions are charged. So what do you know about charges? They conduct. They conduct. Okay. So I have here a conductivity. Here it is. So basically, I have two wires that come together, joined together in this light bulb. Okay, let me put a power source to it. So sodium chloride, which is here, contains what two ions? Sodium ion, which is +1. It's group 1 in the periodic table. And what else? Very good. Chloride ion, which is group 7 in the periodic table. So what do we know about ions? They give off electrons or they take electrons. And electrons conduct. So let's see what happens if I put this in this sodium chloride solution, which is solute plus solvent. So what's doing the conducting? The ions. Okay, the ions. Okay, so we say this solution is a conducting solution, or also known as electrolytic. Have you heard of electrolytes? Like the Gatorade, okay? Gatorade or Powerade or a bunch of other things. What do they contain? Electrolytes, yeah. What are those electrolytes? I don't know, maybe sodium ion, chloride ion, okay. I think the exercise kinesiologists should know, right? Let's say that. Anyways, the athletes may know that are hydrating or they do dieting, nutrition. So we can call not just sodium chloride in water a solution, we can call it an electrolytic solution. Also conducting or conductive solution. So this is something that may confuse you guys, but if I take NaCl and I dissolve it in water and it dissolved perfectly and cleanly and nicely, I have sodium chloride aqueous. Okay, but sodium chloride aqueous is really what? What's causing this to light up? What's causing it to light up? Yes, David, the ions. Okay, so sodium chloride aqueous is nothing more than sodium ion plus chloride ion. So what's inside here besides water? Sodium ion and chloride ion. That's why the light bulb lights up. So this happens in an ionic solution. What about the sugar water, which is covalent? Do you remember what covalent means? They don't exchange electrons, but they do what? They share electrons. So what happens if I put it in here?
It's not the light on.
Will the light turn on or off? Why is it? What's happening?
There's no ion.
There's no ions. So we can call glucose in water. Okay, this is actually sucrose, but sucrose contains glucose. So this is glucose in water is non-electrolytic and non-conducting. Okay. Right, you agree it's non-electrolytic? Are there any electrolytes in here, in the glucose water? No. So it's non-electrolytic and non-conducting. Solution. Okay, but it does go in solution. Okay, this kind of makes it really good. It does go into solution. But what is glucose in water then? So what is glucose in water? Glucose in water just is that, glucose in water. It does not dissociate. It's just sugar water. This dissociates into its ions because it's ionic. This is just dissolved in water. So this is what we would expect for something that's covalent. Nothing, just it dissolves. For something that's ionic, okay, the water has this strange capability to dissociate or solvate. So it's actually dissociation. Into its component ions. Right, so any ionic compound, would it be conductive? Yes or no?
Yes.
Would it be electrolytic? Yes. Okay, anything covalent, you dissolve it in water and make an aqueous solution. Would it be conductive? No. No. Okay. So anything covalent in water is non-conductive. Anything ionic in water, what will it do? It will break it apart into what?
Ion.
Into its ions. It will break it apart into its ions. Okay. All right, so that's the important take-home message for this one. Let's do a little reaction together. Okay. And then I'll let you guys go. Let's do a reaction. Okay. Here I have 0.2 big M, that means molar. We'll talk about that later in the chapter. But I got barium nitrate, BaNO3. BaNO3 2. Okay, barium nitrate. Is this solid, liquid, gas, or aqueous?
Aqueous.
So it has some barium nitrate dissolved in water. The concentration is 0.2 moles over liter. 0.2 moles over liter. Okay, and solid, liquid, or gas?
Liquid.
No, solid, liquid, gas, or aqueous? Aqueous. Okay, so barium nitrate in water. Okay, is it soluble? It is soluble. Okay, so one thing I want you to know when it comes to solubility is that all nitrates are soluble. All nitrates are soluble. So is barium nitrate soluble?
Yes.
You can see it. Okay, it's just water which has barium nitrate. Is lithium nitrate soluble? Calcium nitrate? Magnesium nitrate? They'll all go like this. Okay, iron 2 nitrate?
Yeah.
All nitrates are soluble. So those 4 words I'd like for you to memorize. All nitrates are soluble. All right, so we have barium nitrate aqueous. Let's mix that in with some, same thing, 0.2 big M moles over liter sodium sulfate. Okay. So we have here sodium sulfate. Okay, is this solid, liquid, gas, or aqueous? This is some sodium sulfate mixed with water. It's aqueous. Okay, don't say liquid. Okay, there's some sodium sulfate dissolved in this small amount of liquid. Okay. Huh? Sorry? Oh, bless you.
Thank you.
You're welcome. Okay, sodium sulfate. All right, it's aqueous. So what we're going to do now is we're going to mix them up. Okay, we'll mix them up. Okay, so you want to mix this, Emily? Or anybody want to come up and mix it? You don't want to come up and mix it? Okay, you just pour one into the other. Brave man. Okay, so we'll take some barium nitrate. Do I have a container here? No, that's fine. Okay, we'll just, okay, one on the other. Okay. And you know what? Just pour one into the other. Okay, make sure everyone in the class can see it. So he's going to take a little bit of sodium sulfate and mix it in with a little bit of barium nitrate. Go ahead, David, and then make sure you show it to the class. What do you think happened? Just maybe want to rock around and show it. He's doing my job. Okay, what do you guys see there? Okay. Milky white. That's a good one. Yep. Milky white. Oh, just walk it around to the whole class. All right, we mixed some of those 2 things there, barium nitrate and sodium sulfate. Thank you, David. Okay, what do you guys see here? Something that's milky white. Definitely not in solution. Okay, let it settle. Let it settle for a day. We'll see what happens. You get something that's milky white. Okay. First chemical reaction. So we mix these 2 together and we get something that's milky white. So what is this reaction and what are the products? We mix those 2 up. Barium nitrate and sodium sulfate. All right. Before I let you guys leave, we're going to figure out what this reaction is. Okay, what's going on here? So barium nitrate, is it ionic or... So what do we say about ionic compounds in water? They go down into their ions, okay? Sodium sulfate, it's in water, it goes down to its ions. Ionic compounds do this, okay? So now you have something with barium ion and nitrate ion, sodium ion and sulfate ion. Okay, the ions will mix, pluses will interact with the minuses. So this sodium ion and nitrate ion will come together. But what did we say about sodium nitrate? It dissolved in water, so all nitrates are soluble. And since all nitrates are soluble, it just breaks apart into its ions. Okay, what about this? Barium sulfate. Okay, what do we know about sulfates? Okay. So I'll bring you a solubility table. It's hard to see, but anyways. And I'll give you one for the test that you can use. In the solubility table, you'll find that barium sulfate is insoluble. Okay. So what is the identity of this? This is barium sulfate, and what is its state? Solid, liquid, or aqueous? It's not a liquid. This is solid barium sulfate. It's not soluble. Okay, let this settle. Okay, it will settle, and then you'll see the barium sulfate is solid. Okay. Sorry?
You sink to the bottom.
It will sink to the bottom. This is called a precipitate. So what's the identity of this milky white precipitate?
A solution.
What's the identity of this precipitate? Barium sulfate. And what is its state? Solid. Okay. So how do we know when something is soluble or insoluble? We use something called the solubility table. So I have a better one. I'll give that to you on class Thursday. Bring it to the exam. Okay, bring it to the exam. Okay, so you can bring it to the exam. I'll get you one. Okay, finally, I just wanted to say one more thing here. The NO3s and NO3s cancel. The sodium cancels. So the net ionic equation for this is barium ion plus sulfate ion gives you barium sulfate. Okay, so this is what we're going to call the net ionic equation. Okay, more on this Thursday. So this is called a double displacement reaction. So this is something we'll talk more about, like I said, in our next class. You'll see this milky white precipitate, which is called barium sulfate. The identity is barium sulfate because it is insoluble. Okay, it's insoluble. So it's not that we have to memorize this. Do not memorize this. Okay, I'll get you the table. But we want to know what's soluble and what's insoluble. In terms of the solubility table, what 4 words I think you should memorize? All nitrates are soluble. Remember that. Anything else? You just use this table. I'll give you the table Thursday.
Thank you.
Wait, let me give you your exam.